Okay, now I think it's visible. Okay, we have discussed till this
Yes,
point
sir.
in the last class, and this is one of the example which I is given, and you will find that there is a rule which gives that you are finding the support and the confidence of the rule. This rule. That means BD follows A. That means if there is a BD, there is also an A, and you want to find the support of this rule as well as the confidence of this rule. Now let us try to find the support. Now you find BDA is here, you find that BDA is here, you also find that BDA is here. That means you are having 3. And out of 3, you will be having, out of 4 you are having 3. Therefore the support if I take, it will be 75%. It will be 75% by 3 by 4. Now let us try to find the confidence of the rule. Now, for the confidence, you have to first of all check the left hand side. That means the support of the BDA divided by support of BD. Support of BDA divided by support of BD. Now what is the support of BDA? 3. What is the support of BD? Okay, tell me what is support of BD? B comma D.
3 only.
3 only, because they
3.
are transitions. Therefore, the support of BD is also 3 and the support of BD is also 3. Therefore, the confidence will become equal to 100%. It will be 100%. It will be 100%. Because it is 3 by 3. And therefore, this is how you are going to calculate the support and the confidence of any particular rules which you find from the database, and try to analyze that this is an interesting rule. Okay. Now, this is the formula which we applied, and it will be something, this will be 100%, which we have already discussed. Now, this is the formula, and if you want to find the confidence of any rule, that x follows y, you can find the support of x union y divided by support of x. Okay, this is a simple formula. That means you have to find the support of all the items in the rule divided by the items on the left hand side of the rule. That means support of x union y by support of x. Okay. Now, whenever we are given a set of transactions, the goal of the association rule mining is to find all rules having a support greater than equal to mean support and confidence greater than equal to mean confidence. Now, this is the general association rule mining task. That you are given a set of transactions T, and you have to find all the rules which are having a support given that the minimum threshold value is given by the user and the minimum confidence is also given by the user. And you have to find that which are the rules which have this many support and this many confidence. Okay. Therefore, these two measures of support and confidence are the measures of interestingness of the rules. This is support and confidence are the measures of rule interestingness. Okay, that means they are going to reflect the usefulness and the certainty of the discovered rules. Okay, they are going to find the usefulness and the certainty of the given rules. Now, how we are going to do that? Let us try to give a brute force approach. Brute force approach means how you are going to use with all transactions which are given, and you are going to find all the rules. Now, what we can do is that we have to find all the possible association rules and then find the support and the confidence of all of them. Then delete all those rules which are not having the minimum support and minimum confidence. And whatever remains over there will be the rules which are satisfying these conditions. Therefore, this particular concept is fine. It will work perfectly, but it is not easy and almost impossible to do that. Why? Because it is computationally very, very time-taking and is prohibitive. That means the time taken as and when the number of items will keep on increasing, this will become impossible for you to calculate. And why I say impossible, you will come to the conclusion when I will show you the true figure when it comes to a particular simple departmental store which only contains 100 items. And with 100 items only, this rule of finding this will fail miserably, and you cannot find the association rules from there. Now let us see what we have done. These are the transactions, and we are finding these rules, some of the rules, not all, but we are finding some of the rules, and calculate the support and the confidence of all these rules. Now when I am going to do this, I get the support of 0.4 and the confidence will be either 0.5 or 0.67 or 1, and I get all this. Now suppose I give a support of equal to 0.4 and a confidence of say 0.67. Now in that case, if I am going to do this, I will be ending up in getting this one, this one, this one, and this one. Whereas these two rules will be pruned because the confidence is less than 0.67, and therefore I will end up in finding these many rules, these 4 rules. But the problem is that how many items you had? You had only 6 items: bread, milk, diaper, beer, eggs, and coke. Therefore, this is too easy. But even in that case, these are not the only rules we will find. This is just a few rules which I have discussed. Now let us try to come up with the actual figure what will happen. Now when you are going to use for such rules, you are going to try to find all those rules which are discovered from these item sets. Now if you find on the left hand side, you find that milk, diaper, and beer are all binary partitions of the same item sets. Therefore, the support will be same. Now what I am trying to make you feel that why the support is same. Because milk, diaper, beer are all binary partitions of the same item set. Why I say binary partition? Because you are trying to divide these 3 items into 2 subsets, where one subset could be milk, diaper, and beer, other subset might be beer, milk, diaper, or so on. Therefore, when we are finding rules which are originating from the same item sets, they will have identical support, but will have different confidence. Okay. Therefore, what we have to do is that we have to decouple the support of the confidence requirement, because you have to give a different support and a different confidence. Now, what you can do is that you have a 2-step approach. That means, first of all, you generate all item sets whose support is greater than mean support, and don't go for those item sets which are binary partition of the same item sets. And then you generate rules which are having high confidence, and then you are going to get some lesser rules than what you got in the last time. But even this is not very computationally expensive, because in that case also you will end up in getting many rules which are not at all required or not at all interesting. Now let us come to this figure which tells the whole story. Now suppose you are given 5 items, and these are the 5 items over here. These are the 5 items, and you want to generate all the possible candidate item sets. Now you will if I am going to use this, I will generate 2 to the power of 5 possible items, candidate items. And this is the lattice which shows you how you are going to generate. You start from null, then you have A, B, C, D, E, then you combine A with B, A with C, A with D, A with E. Similarly, you will say B, C, B, D, B, E, C, D, C, and D. That means at this level, you are going to generate all combinations of A, B, C, D, E with 2 items. That means we are trying to find it with K is equal to 2. Then at the third, at this place, you are going to combine AB, AC, AD, AE, and all those such that you generated 3 item sets. and you have to make sure that when you are joining those 3 item sets, you can only join those 3 item sets with those ones which are having at least one common. Now, if you see from this figure, you will see that AB is not combined with CD. Okay, AB is not combined with CD. Now, why it is like this? Now, let us try to show you. See, AB is not combined with CD. There is no arrow from AB and CD which are merging anywhere. Why? Can anybody give a reason that why AB and CD is not combined together?
सर क्योंकि सर अलग तीन सेट नहीं बनेगा ना, तीन एलिमेंट सेट नहीं बनेगा, चार एलिमेंट हो जाएंगे ए बी सी और डी.
Because when you combine 2 item sets, you have to combine over one common item set. Just like what you do in a database. When you perform a join on some common attribute. Therefore, if I join AB with CD, I have no common attribute. Therefore, whenever you join AB with AC, you will get ABC. When you join these two, you get AC, ABC. When you join AB with AD, you get ABD. And similarly, when you join AB with AE, you get AB, and so on. That means you will only generate these 10 3-item sets. And similarly, at this step, you are generating 4-item sets. When you combine 3 with 3 over 2 item sets, that means you can combine, say, ABC with ACD over AC. For example, I can combine this one and I can combine this one over AC. Therefore, what I will get? ABCD. Because AB is common, I will take ABC with ACD and I will get ABCD. This simple join what you have been using in a database in the last semester. And you will come to know when I go for the algorithm, you will find that I am just using a simple join, which is nothing but a self join. It is a self join. You know self join, you join the item set over itself. Okay. Now, I get these item sets, 5 item sets, which are basically combination of 3 item sets over another 3 item set with 2 in common. And the last one, I get nothing but the whole superset of ABCD. And then I get 2 to the power of 5 possible item sets out of 5. That means 2 to the power of 5 is 32. But if you find over here, now the problem is that are all these rules are really useful? Okay, you do not require this rule. Even you do not require this rule because it is not a single item sets will not generate any rules. And also you do not require this rule. Why? Because ABCD, if you take on the left hand side, nothing is there on the right hand side. And therefore, I can remove those 7 rules, 7 item sets. Then all those which are remaining over there, I have to find the support and the confidence, and then I have to use. I can prune those item sets which do not have the minimum support and the minimum confidence. Okay. But even this is not a very good thing because this will again generate lot of different rules. Now, if you see out of 32, you have just removed 7. Then also you will end up in having 25 different rule support and the confidence. Okay. Now let us try to make it more shorter. Now, what I am going to do over here, that when I apply a brute force technique, what I will have an item set, which is a lattice of all candidate frequent item sets. Then I count the support of each candidate by scanning the database. And from there, I get the list of candidates. Then, what I am going to do, I will match each transaction against every candidate. And the complexity of the whole algorithm is given by order of n into m into w. Now, NMW stands for n is the number of transactions, w is the width of transactions, that means how many transactions are there in one item. So, what is the maximum number of transactions? Sorry, what are the maximum number of items in any transactions? Now here W is equal to 4 because the maximum length of any transaction is 4 and M is the number of candidates, and therefore it is nothing but N into M into W. But if you find that M is 2 to the power D, already discussed in the last slide. Therefore, if you multiply N into M into W, this again becomes a 2 to the power D multiplied by N multiplied by W. Even if N and M are small numbers, 2 to the power D is a very large number. The 2 to the power D is a large number because the number of items may become say 10, 20, 30, 40, 50. If D becomes 100, this is nothing but 2 to the power 100 multiplied by N multiplied by W. And 2 to the power 100 is such a big number that even if N and W is equal to 1 also makes no difference. Okay? If they are even a very small number, then also it is not going to affect much on the overall complexity. Therefore, the whole complexity revolves around the value of M. And M is very, very large number. Now this is the brute force technique. Now this we will try to understand that why this particular number computational complexity becomes so large. Now if I draw this, if I see this particular graph, this is D, and these are the number of rules. And you find that if D becomes 6, the number of rules is small. But if D becomes 10, the number of rules reaches to the value of around 5 into 10 to the power of 4. Even if D is equal to 5, this becomes if D is equal to 10, the number of rules you generate will become 5 into 10 to the power of 4. Because if you are going to draw a line from here, it's somewhere like this. And this value what you get over here will be something around 5 into 10 to the power of 4. If D becomes say 20, this value will become much larger. And this is the formula which is used to calculate the number of rules. That means even if D is equal to 6, this formula will result into 602 rules. Now if D is equal to 20, this becomes 3 to the power 20 minus 2 to the power of 21, which is also a very, very large number. It becomes millions and millions. If D becomes say hundreds, it is almost impossible to find that. And therefore, and you will be surprised to know if D becomes 100, the number of rules that we generate will be order of 10 to the power of 30. Will be on the order of 10 to the power of 30. To be precise, it will be equal to around 1.27 multiplied by 10 to the power of 30. And you can know can you calculate the confidence and support of 10 to the power 30 rules? No. It's highly impossible. And also, it is also what I am telling only for the 100 item sets. Now, any particular departmental store will have thousands of item sets, not only 100 item sets. Therefore, this value it is highly impossible to come with this. Now, you might ask a question that why we are studying all this if it is not feasible. Of course, when we know that it is not feasible, then only we try to find a better algorithm for this. And therefore, this is just to show you that this ARM is not, you cannot apply a brute force technique on the ARM. You have to try to find a particular algorithm which should scale well. When the number of this item sets keeps on increasing, it should scale well. And the algorithm should be scalable. And this algorithm, what we are going to discuss today, which we discuss right now, is not at all scalable. It will work for a very small data set. Okay. Now, once we are now how to reduce that? In order to reduce that, we have only 3 things what we can do. We can reduce the number of candidates, that is M. or reduce the number of transactions, n, or reduce the number of comparisons, that is n into m. Now you know that the complexity is n into m into w. Therefore, how will you going to do that? You can reduce either m and you can reduce n, or you reduce nm. But if you reduce m, and you know that m is the one which is contributing to most, therefore if I reduce m, the complexity might become less. Is it clear that m is equal to 2d? If m is equal to 2d, if I reduce m, I will be able to find a better algorithm. Therefore, reducing n is not needed right now, because if n is large, even if you reduce n, it is not going to affect much. But if you reduce m, you will end up in reducing the number of candidates, as well as you will also reduce the number of comparisons, because m is coming here also and m is coming here also. And therefore, my aim will be to reduce m and not directly to reduce n. Okay? But how can I do? If I want to reduce m, I use some pruning techniques. We'll discuss that right now. If I am going to reduce the n, I have to use some method which we discussed in the algorithm. It is called a vertical based mining. That is called a vertical based mining. This mining, what we are trying to do, is called the horizontal based. Why it is called horizontal based? Because in the data set, you will have one column as the transactions and other columns as the items. If I am having a vertical data set, it will be items on the one column and the transactions which are occurring for that item set in the next column. Did you get it? The difference between horizontal and vertical based mining. In horizontal based mining, you will be it will be something like this. That you will be having a TID over here and item set over here. And this is the horizontal based mining. If I am shifting it to vertical based mining, the TID will be replaced by items. It will be replaced by items. And this item will be replaced by transactions. That means if I write in the left hand side, if I write bread, what will the transactions over there? It will be T1, T2, T4, T5. Got it? That if I am converting this vertical horizontal based data set to a vertical data set, what I will do? In the left hand side, I will write bread, milk, diaper, beer, egg, and coke. I will have 6 items. And the transactions which are there in the 6 items: bread 1, 2, 4, 5, milk 1, 3, 4, 5, diaper 2, 3, 4, 5, beer 2, 3, 4, and so on. If this is if I am going to maintain like this, it is called a vertical database mining. But if you want to convert a horizontal data set into a vertical data set, you require just one scan of you have to use only one scan of the data set. And with a one scan of the data set, you can convert a horizontal data set to a vertical data set. Is it clear to you? That I can just scan the data set and I can know that there are 6 items. I maintain a table with 6 items and keep on reading the transactions over there and just try to put those transactions in the corresponding items. And I can do it in one transaction, one scan. Okay. Now, how to reduce the number of comparisons, I can use some efficient data structures to store the candidates. I can use the hash-based technique. Some of you might be knowing what is the hashing technique, and we'll discuss over here. You can use a good hashing method, and I don't need to match every candidate against every transaction. Now, this is a very important observation. That means I don't need to match every candidate against every transaction. Okay, fine. Okay. Now today, this is the first algorithm which I am going to discuss, the trolley algorithm. In the next lab, prepare yourself for this algorithm for the programming. that you will be given to program the priority algorithm. This is the first assignment of your lab on Monday. Now the priority principle says that if an item set is frequent, then all of its subsets must also be frequent. Now it's a very simple statement that if I find that A, B, C, D is frequent, all its subset, that means subset of A, B, C, D, AB, AC, AD, BC, BD, ABC, BCD are all frequent. That means the priority principle is simple. It says that for all x comma y, x is a subset of y. Therefore, the support of x is always greater than or equal to support of y. That means for all x comma y, where x is a proper subset of y, then support of x will always be greater than or equal to support of y. When x is a subset of y. Okay. If both are same, then also it will be support of them. This will be same. Now try to understand it very well, because in this particular concept, the algorithms which we are going to discuss will be based upon. Is it clear that for all x comma y, the support of, now what I can say in the other way, the support of an item set never exceeds the support of its subsets. That means the subset support whatever is there, the support of any item set will never exceed the support of its subset. Now what I am trying to say, the support of AB is say 20. Or I say 20%. 20 means 20%. The support of AB is 20%. Then any superset of AB will be having a maximum support of 20% only. Okay. Any superset of AB. What are superset of AB? ABC, ABD, ABCD, any superset. Or I can say in the other way around, the support of a particular item set will always be less than or equal to the support of its subset. And this property is called as the anti-monotone property. The anti-monotone property of support, that means the support of an item set never exceeds the support of its subset. And using this anti-monotone property, we are trying to write an a priori algorithm. Now, Rakesh Agarwal and Shrikant, they are the one who gave this a priori algorithm, and just I'll try to show you the algorithm. Now, this is the thing what I discussed, that if I calculate the support of bread, this support of bread will always be greater than support of bread comma beer. It could be equal also, but here it may not be. Now, what is the support of bread? It is 4. What is support of bread comma beer? It is 1, 2. Therefore, if you see over here, this support is equal to say 4, and this support is equal to 2. What is support of milk? Again, it is 4. What is support of bread comma milk? Just calculate 3. Diaper comma beer is 1, 2, 3. Diaper comma beer comma coke, you see, 1. In some cases, this could be equal also, but the left hand side will always be bigger than or equal to the right hand side. The right hand side can never be bigger than the left hand side. And this property is called as the anti-monotone property of support. Okay. Now let us try to apply this property on the lattice what we have shown earlier. So this was a lattice which I showed you. Now what I am going to do, I am trying to calculate the support of the first level. That means I am going to find the support of these item sets. AB, AC, AD, AC, and all item sets. And then I find that AB is infrequent. It is not frequent. Now, if it is not, AB is infrequent, all supersets of AB will also be infrequent, because the a priori property will hold. And therefore, what I can do is that I can remove this, I can remove this, I can remove this, I can remove this. Why? Because these all condense AB. If support of AB is less than the minimum support, the support of ABC will always be less than the support of AB. Therefore, these 7 item sets will be pruned from the lattice, and what ultimately remains is the remaining ones. Is it clear to you? Is this clear?
Yes, sir.
That I calculate the support of AB. If I find that support of AB is not equal to the minimum support what is defined by the user, I don't need to generate the supersets of AB. I don't need to generate. Here I generated because it was already there in the lattice. But actually in the a priori principle I will not generate ABC, ABD, AB, and I will not generate these. Similarly, if I find that BD is not frequent, I will remove this BD, I will remove this BD, I will remove this BD. And whatever remains, suppose if I find that now all are having minimum support. Now how many rules I got? I will get only over here. I start over here 1. Now I'll get 2. I will get 3 items. Then the 4. Then I will have this 5. Then 6. Then 7. 8. Then I will have this 9. 10. This 11. This 12. And this 13. And this 14. That means I have from 32 I got only 14 because I have used a pruning method. Got it? Now, what are the item sets I got? 2 item sets. What are 2 item sets? AC, AD, AE, BC, DE, CD, CE, and DE. 3 item sets. ACD, ACE, AD, DC, and 3D. 4 item sets. ACDE. Okay, fine. Is it clear? Okay, now let us try to come to the next slide. Now this is what I pruned. I already showed you that I am pruning this whole item sets because here I am pruning, but in the a priori algorithm I will not generate itself. Okay. Now let us try to understand the a priori principle. Now suppose this is given. This is the items I generate from the table, and I generate bread count is equal to 4, Coke is 2, milk is 4, beer is 3, and so on. And this has been generated from the particular table which was showed to you earlier. I count all the occurrence of bread 4. I count the occurrence of Coke is equal to 2, and I take some minimum support. Now this minimum support is user defined. It means this support is given by you. And what I am going to do, I am having the support of this value. Therefore, what I am going to do is that I am removing those item sets which are less than equal to 3. And therefore, here this will be removed because it is having 1, and this will be removed. That means if I remove Coke and eggs, I will be ending up into getting only 4 item sets and no further item set will contain Coke and X. Okay, fine. Now let us try to generate the pairs. How will I generate? Bread milk, bread diaper, bread beer, milk beer, milk diaper, and beer diaper. How many I will get? I will get 6. First one with 3, second with 2, third one with 1, and so on. Therefore, I generate all the possible 2 item sets pairs over here. And then again I find the count of bread, bread milk, bread beer, bread diaper, and keep on counting from where? From this data set. From here. From here. I am going to use the count. Now when I am going to do this, what you find that I am scanning the database again. I am trying to scan the database again. And therefore, what I am going to do, when I count, I find that this is 2. Therefore, I remove this. Again, this is 2. I remove this. And then I again find the triple item set. That will be triplets. Again, I told you how will you going to do? You will combine bread milk with bread diaper, and you will get bread milk diaper. Then you are going to combine this with this. You are combining this with this, and you are combining this with this. You combine bread with milk, with bread and diaper, you will get bread milk diaper. You combine bread milk with milk diaper, you get bread milk diaper. You combine bread milk with beer diaper, you can't, because there is nothing in common. Therefore, what is happening is that here we cannot, we are not, it's not possible for you to do this. Therefore, this is not, you cannot do this. You cannot do. Because there is nothing common. Therefore, you cannot combine bread milk with beer diaper. Then again, you are going to combine this beer diaper with milk diaper, and this beer diaper with bread diaper with beer diaper. When you combine bread diaper with milk diaper, you again get bread milk diaper. This is already there. This is already there. Then you again combine bread diaper with beer diaper. You will get bread beer diaper. Okay, and then you are going to combine milk diaper with beer diaper. You will get milk diaper and beer. Now, when you find that the support of the rules of bread diaper and milk and diaper is 3. Whereas if you calculate, if you are going to combine these two, you will get milk diaper beer. When you are going to combine these two, you will get milk, beer, and diaper. Now you calculate over here. How many times bread milk diaper is coming? It's only coming 2 times. Okay, bread milk diaper is coming 2 times, and therefore this does not support the minimum support value. Therefore, what I end up in getting only one of them. I'll get only one of them, and by this method, you are ending up in getting the number of how many number of item sets you are getting. You are getting only 4 at the top and 1 at this. Therefore, you are only getting 5 item sets, which are either 2 item sets or 3 item sets. Okay. Now, based on this one, if somebody is trying to join. Okay. Now there are 3 item sets. Now this is algorithm, and now just try to convert this algorithm into a formal algorithm. It's too simple. Now this is a priori algorithm. Now what I said, I'm just trying to put into an algorithmic form. Now what you do is that find frequent 1 item set and put them into L of k. Now L of k is nothing but the item sets of length 1. because you are having one item set. Then you are going to generate now these item sets are the one which are frequent. Now use LK to generate a candidate item set of C of K plus 1. Now what I am going to do, using L1, I generate C2. Now what is C and L? L are the ones which are already past the minimum support and minimum confidence. Minimum support, sorry, not confidence, minimum support. I'm not considering the confidence at this moment. Now, what is C2? It are candidates which have been generated. I do not know whether they are frequent or not. They are not frequent. Now, I'm using L1 to generate C2. Now again, I scan the database to find which item sets in C2 are frequent. And if they are frequent, I generate L2 from C2. Now L2 are the one which has passed the minimum support. C2 are the one which are generated from L1. Now again I will try to generate from here. I will generate C3. And from C3, I will again scan the database and try to find L3. From C3, I again try to generate C4. And suppose if C4 becomes equal to null, it becomes null. It means that you cannot generate any more L and you stop at this moment. A time will come when you will have a null set at C4, or you will have only a single set from that you have to check. If it is null set, you stop. Otherwise, you again keep on going, generate L4, from L4 to L5, C5, from C5 to L5, and keep on going. Therefore, what I am going to do, if I am going to use this, if LK1 plus is not empty, you increase K and you loop from here to here. Loop from here to here. Otherwise, if it is empty, the algorithm terminates. And you will end up in finding. Now, what are the frequent items over here? Anybody? What are the frequent items which are found? Tell me, what are the frequent items set which are found over here? I can expect that one of you should answer this. It's nothing but L1 union L2 union L3. And these are the frequent item sets which has been generated. That means it is nothing but the set of all one item sets, the set of all two item sets, and the set of all three item sets. In case you are not interested with L1, you just try to do L2 union L3. That means in the end I will get L1 union L2 union L3 dot 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 L of K. And this is the whole algorithm of a priori algorithm given by Srikanth and Agarwal in the VLW conference in 1994. Is this clear? Okay. Now what I can do is that this algorithm is already known to you, and now you can directly write the algorithm. Now let me try to show you how you are going to write the algorithm. Again, it's simple task. Now this is the pseudocode for this. Now you start with CK. CK means the item sets which are being used, which are the candidates. Candidates are the one we do not pass the minimum support, and LK are the frequent ones. Therefore, we start with L1 which are the frequent items. Initially, which is a one item set. Then for k is equal to 1, Lk of not equal to phi k plus plus, you are going to generate Lk is this C of k plus 1 from Lk. And how you can do? You are going to make a join. Now here I am going to say you are going to do L1 and you are going to do a self join with L1. And you are doing a self join over there. You are going to join L1 with L1. And then once you are going to do, you will get what you will get? You will get C2. And with C2, again scan the database to check whether which are the item sets, which are the transactions which are frequent. And I start pruning if it is not there. And once what I am left from there, I will just write to be L2. And again I will make a join with this with L2 and generate C3. And you find what I am going to now here you should be able to see what I intended to do and what I got. See. What I am returning? L of k union over k. That means k is equal to 1. I am trying to L1 union L2 union L3 dot 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 L of k. And that is the last thing what I get. Is a priori I get a set of all LKs which are basically frequents. Any questions you want to ask? I think this should be clear to you. The important step in the candidate generation is that the join step, when you are joining C of k plus, you are joining LK with itself to generate C plus k. This is what I try to show you. This is what is self join. And the Purna step is the one where I am converting from the C2 to L2. This is the Purna step. That means any k item set that is not frequent cannot be subset of a frequent k plus 1 item set. That means once I am converting from C2 to L2, I am pruning. Therefore, the join step is this one. This is the join step. And this is the Purna step.